All right, let's jump right into this explainer. We're talking acids, bases, and salts today. So whether you're just building your foundational knowledge from scratch or you're desperately trying to get prepped for your exams, you are in the exact right place. Seriously, we're going to break down everything from the chemistry of the lemon in your fridge to the literal plaster that sets a broken bone.
Think of this as your ultimate cheat sheet. We're splitting this whole battle of chemicals into 5 super quick modules: meet acids and bases, the color-changing indicators, epic chemical reactions, the pH power scale, and finally, essential salts and compounds. Let's get right to it.
Module 1. Meet acids and bases, the main characters. We're kicking things off by unmasking our 2 heavyweight contenders.
Okay, so this perfectly captures the sharp contrast between our 2 rivals. Acids are basically substances that donate H+ ions, hydrogen ions, when you dissolve them in water. If you were to taste them, well, think of biting into a raw lemon, right? They've got a really distinct sour taste. And if we test them with litmus paper, acids turn blue litmus paper a bright warning red. Bases, on the other hand, are our OH- donors. They release hydroxide ions. Have you ever accidentally gotten a bit of soap in your mouth while showering? Yeah. Then you know exactly what a base tastes like. It is incredibly bitter. They also feel kind of slippery or soapy to the touch, and in a total reversal from acids, they turn red litmus paper blue.
Now, you're definitely going to need to identify naturally occurring acids for your exams, so here is a fantastic little trick for you. To memorize these, just remember the phrase very, very acidic orange city for the first 2. Vinegar has acetic acid, and orange has citric acid. Got it? For the next 2, imagine turning down a game of table tennis by saying TT tomorrow. The TT stands for tamarind containing tartaric acid, and tomorrow stands for tomato containing oxalic acid. Lock those into your memory right now, and you are going to easily ace those multiple choice questions.
Module 2. The color-changing indicators, revealing the truth. What's super interesting here is how we figure out what these invisible chemicals are using their color-changing friends.
Obviously, we can't just go around tasting mysterious chemicals to see if they're sour or bitter. That's, incredibly dangerous. So instead, we use indicators. Just like friends who completely change their true colors when trouble hits, indicators are substances that expose whether we're dealing with an acid or a base by drastically changing their own color or sometimes even their smell.
You absolutely must memorize this chart. These are our synthetic, human-made indicators. Take phenolphthalein, for example. In a neutral or acidic solution, it's completely colorless. Looks exactly like water, but magically, the very second a base arrives, bam, it turns a bright, shocking pink. Then we've got methyl orange. As the name implies, it starts orange, but drop it into a dangerous acid and it turns red. Drop it in a base, though, and it shifts to yellow.
But hey, what if you're more about smells than colors? That brings us to olfactory indicators. If you take onion, vanilla extract, or clove oil, which all have very strong, very distinct smells, and you add a base to them, their scent completely disappears. Seriously, imagine taking really sweet-smelling vanilla, dropping a base on it, and suddenly, just nothing. It's an unbelievable chemical disappearing act.
Module 3. Epic Chemical Reactions, the Battle Arena. Let's see what actually happens when our acids and bases start clashing with other stuff.
So, when acids react with metal carbonates or metal bicarbonates, they always produce 3 things: salt, water, and carbon dioxide gas. We actually test for this CO2 using the famous lime water test. When you pass that CO2 gas through clear lime water, it instantly turns milky white because it forms calcium carbonate. But here is the real magic trick. If you keep going, like if you add excess CO2, that milky white solution becomes completely clear again. That's because it forms calcium bicarbonate, which is fully soluble in water. It's literally chemistry acting like a magic show.
Bases have their own unique reactions too. When a strong base, like sodium hydroxide, reacts with a metal, like zinc, it forms a salt and hydrogen gas. But the specific salt it forms is famously tricky for students to remember. It forms sodium zincate. But you can easily remember the chemical formula using a fun little trick. Natu. The formula is Na2ZNO2. Natu. See what we did there? Remember that, and you'll never forget the formula for sodium zincate.
Module 4. The pH power scale, measuring strength. Because it's not enough to just know if something is an acid or a base, right? We need to know its exact power level. Enter the pH scale. pH literally stands for the potential of hydrogen. It's a scale running from 0 to 14 that measures the concentration of H+ ions in a solution. But here's the massive twist that always trips people up. The lower the pH number, the stronger the acid. So a pH of 1 means you have a violently strong acid loaded with H+ ions. A pH of 7 is perfectly neutral, like pure water. And anything above 7 is basic, with 14 being the absolute strongest base.
When we pair the pH scale with a universal indicator, it essentially paints a reverse rainbow to show us exactly how strong a chemical is. Think of a reverse Vibgyor. On the far left, at pH 1, you've got this highly acidic, danger red. As you move towards 7, the colors warm up until you hit a perfectly neutral green. Keep pushing into the basic numbers above 7, and the scale cools down into blue, ultimately hitting a dark violet at pH 14.
And listen, this matters in the real world constantly. Your stomach uses strong hydrochloric acid to digest food, but if the pH drops way too low, you get awful acidity. The fix? You swallow a mild base like milk of magnesia to neutralize it. If a farmer's soil is too acidic, the crops will literally die, so they mix in basic quicklime. The enamel on your teeth starts decaying if the pH in your mouth drops below 5.5, which is exactly why your toothpaste is basic, to fight off that acid. And if a bee stings you, it is injecting actual acid into your skin. Rubbing a basic household item like baking soda right on it neutralizes the venom and stops the pain.
Module 5. Essential Salts and Compounds. The Aftermath. As our acids and bases battle and neutralize each other, they leave behind these powerful artifacts known as salts.
Now, a huge misconception is that all salts are completely neutral. That's only true if the strong acid and a strong base perfectly cancel each other out. But what happens if a strong, heavy-hitting acid clashes with a weak, flimsy base? Well, the resulting salt is still going to carry an acidic punch. It becomes an acidic salt. Conversely, a weak acid reacting with a strong base yields a basic salt. Basically, the stronger chemical always leaves its genetic footprint on the final salt.
Okay, moving to a guaranteed exam topic, the chlor-alkali process. This brilliantly shows how we mass-produce essential chemicals. We take plain old salt water, also known as brine, and we run powerful electricity right through it. This process physically splits the salt water apart into 3 incredibly useful things. Sodium hydroxide gathers near the cathode, chlorine gas bubbles up at the anode, and hydrogen gas escapes at the cathode. And we do not let any of those products go to waste. We take that chlorine gas we just made and pass it over dry slaked lime to create bleaching powder, CaOCl2. This stuff is heavily used in the textile industry and is absolutely incredible for purifying our drinking water. Then we have washing soda. Its formula is Na2CO3.10H2O. That .10H2O is so crucial, it means there are 10 molecules of water crystallized right inside it. Aside from just cleaning your clothes, its real superpower is softening hard water, which makes it incredibly valuable in the glass, soap, and paper industries.
Next up is baking soda, sodium hydrogen carbonate. When you heat this up in the oven, it releases carbon dioxide gas, which gets trapped in the dough and makes your cakes perfectly fluffy and spongy. And because it rapidly releases CO2, it's also a primary ingredient in fire extinguishers. Finally, we have plaster of Paris. When you precisely heat a mineral called gypsum, it loses some of its water molecules and becomes calcium sulfate hemihydrate, meaning it only has half a water molecule attached. When doctors mix this dry powder with water, it sets rock hard to support fractured bones, or even to create the smooth ceilings in your house.
Which brings us to a final thought to leave you with today. We know that heating gypsum carefully gives us plaster of Paris by removing water. But what actually happens chemically the exact moment a doctor adds water back into that plaster of Paris to fix your broken arm? Think about how these chemical reactions can totally reverse and lock into place. Master these concepts, prove the doubters wrong, ace your exam, and use everything we covered today to show them exactly what you are made of.